team will tell us interacting vortices in Yoonbai itself.
I have a kind of a first break in this year after I'm involved in some business. So I would like to thank to the organizers. Today I will talk about today I will talk about the interacting vortices, which means not BPS objects. This work is in the middle of collaboration with Sungkyunkwan and Yoonbai, is my student. First, I will start with a textbook level review about Nielsen-Olesen vortices. So Nielsen-Olesen vortex is a point-like object in a plane. So which is a stringy object, a small one. So this cosmic string can be studied by this point-like object in a plane. So simplest model of this vortices is the abelian Higgs model. So we have a complex scalar field and a Yuan gauge field with a Higgs mechanism here. So the action is very simple. So for more simplicity, I assume about the Mexican heptide potential. So then the energy per unit length along the straight string can be read like this. If I introduce a magnitude and the phase, then I have photons here. So photons are positive semi-definite. So to get the zero energy configuration for the scalar amplitude, it should have V, and it should be the constant. In addition, the magnetic field should vanish, so I may have this configuration. And then if I plug in this one, then this also should vanish. So I have the vacuum configuration. So the topology of the vacuum is obtained by the super selection rule, which is guaranteed when I have the infinite spatial volume. But nowadays, this becomes dangerous in condensed matter system because the sample size becomes smaller and smaller. And the vacuum manifold is obviously a circle. So then the boundary of the xy plane at infinity is also a circle. So your phase of the complex scalar field maps from S1 to S1. So the non-trivial topology is the first homotopy, which is classified by integer group. Okay, so the well-known example to be a topological soliton is the Nielsen-Olesen vortex. If you consider the n vortices superimposed at the origin, then we may have this one with the real function. So then single valuedness of the field guarantees this n should be a member of an integer group. So then the best way to write down for the n separated vortices in the xy plane, you can use this angle like this. However, at each vortex point, to have the well-defined field, so each field amplitude should vanish at that point. So then the object is classified by the quantized magnetic flux, which is first shell number something. So then what we did during last more than 30 years is we focused on the tractability and also we've been treating limit, theoretically and experimentally. So we chose this relation, which means the Higgs coupling is related to electromagnetic coupling. So then at first, phenomenologically, if you check the mass of the gauge field and the Higgs boson, then they have the same mass. The second one is, under this relation, Bernoulli bound is saturated. So if we consider the energy terms, and then we shuffle them to achieve a lower bound, so-called the Bernoulli bound, then you can reshuffle the terms like this. And the third term vanishes at spatial infinity because the current goes to zero rapidly. Then this magnetic flux is now the quantized value, has the quantized value times the rest energy of each vortex. And the other terms are positive semi-definite. So to get the object whose energy is bounded by the number of the total rest energy of the object, then these two should vanish. So now you have the so-called BPS equations. So then the first equation is solved for the gauge field like this. Now if you plug this configuration into the magnetic field, and then finally you have a second order nonlinear equation, which is not solved yet, probably never. However, the existence and uniqueness of the solutions for the n vortices can be proved. So intriguing thing of this, these objects can be found here. Since this, for the Nielsen-Olesen vortices in BPS limit doesn't have any momentum density, so vanished. However, if you look at these stress tensor components and then reshuffle the terms like this, and then you can find the alternating sign here everywhere. So if you have n vortices, or if you have n anti-vortices, these every component of the stress tensor vanishes everywhere. So no pressure and no stress everywhere, though you have n vortices. So n vortices are non-interacting at all. So then what is more, this is the direction of the string theory. So the model with this fixed coefficient was obtained by urging the n equal to supersymmetry. So from this story to the brains was made. However, if you forget the relativity, and then you may get the same bound for the Lagrangians for static configurations, then this limit is nothing but the limit which characterize the Taiwan superconductor and the Type 2 superconductor. So, what is the physical implication of this limit? Is one of it is like this. If you consider slowly moving vortice, two vortices, and then if they collide head-on, then they do not pass, they do not collide to 180 degrees. Instead, they collide and then goes to 90 degrees. This has lots of implications for the cosmic strings. So if you consider the two cosmic strings, this one is nothing but the collision of the head-on collision of the two vortices. So interconnection should be made. So then if you consider a single cosmic string, and then if they collide like this, and then usually cosmic string loops are produced. So then the scenario becomes like this. So if you have enough cosmic strings, and then they make wiggly and lots of strings, and then they make a network. This is really harmful in the sense of the cosmology, because cosmology is constrained by the cosmic microscopic background radiation. So if you have enough cosmic strings, and then that collides with the observation of the CMBR, so now cosmic strings are dead. Easily dead, so easy. However, nowadays these cosmic strings are considered by some kind of some small people, actually, because if you consider the gravitational waves, and if you discuss about the detection of the gravitational waves, then the serious problem in the experimental side is the only source observed was the black holes or neutron stars. So you can, if you increase the resolution, then you may detect more examples, and then you can make the statistics. However, that is all. So the detection of the gravitational waves, if they cannot find another sources, and then they will just go no way. Nothing new, I mean qualitative. So if this one, if the experiment of the gravitational waves become intriguing, they need other sources of the gravitational waves. So if you consider the formation of the curve in the, along the cosmic string, then it radiates huge gravitational waves whose amplitude can be detectable. So this is why some people consider the cosmic strings again. So probably non-BPS. So I will discuss about the non-BPS object first. Let us consider the n superimposed vortices. Then we may use the cylindrical coordinate, and then because of the rotational symmetry, we can choose these ansatz of the field, and the field equations become simple, so they are nonlinear still. So then boundary conditions can be like this. These two boundary conditions can be chosen by the well-definedness of the field. These two boundary conditions at station infinity can be chosen by finiteness of the energy. So then near the origin, you can expand. In a asymptotic region, field approaches the boundary values very rapidly by the mass scales of the gauge field and the Higgs field. So if you do some numerical works, and then you can easily find these configurations given the textbook. But the important thing is this lambda is equal to 1 means, since I chose E is equal to 1, so this green one means BPS object, and these blue one and the red one are not BPS. So if I look at the magnetic field, the magnetic field concentrated near the vortex point, and the energy density look like this. So then if I integrate the solutions, and then if I get the mass means rest energy of n is equal to 1 vortex, then energy is of course increasing if you increase the coupling of the quadratic term of the scalar field. However, if you divide it by the mass of the Higgs field, then it decreases like this. So then, what is the interaction among these n superimposed vortices can be measured by this, maybe this interaction index. So the total energy of the n superimposed vortices is subtracted by single vortex energy times n, and then divided by this two mutual interaction terms. Then we can find this. If you consider the n equal 1 vortex, it should be 0 always. If we consider n equal 2 vortex, and then this one is attractive here, and then repulsive for the large coupling, which is expected, then if I increase the number of vortex, then it slightly decreases like this. If I introduce the rescaled dimensionless field, and then if I consider the interaction terms like this, and I use the equations of motion and the total divergence term, then you can easily find the interactions for between the superimposed vortices is made by cubic or quadratic terms only. So if I consider if I introduce the density of the energy for the interaction, so then for large distance, which means the large rho here, then you can find this cubic terms, actually cubic order. So then if the total coefficient becomes negative, then it means attractive. And if this total coefficient becomes positive, this means positive. However, but if you take long distance limit, and then the signature of the coefficients are important, but the scale determines the attractiveness or the repulsiveness. So if the Higgs mass is larger than the gauge mass, then of course K1 is larger than the K0 here. So if the coefficients signature signs are different, then usually this one is repulsive, which corresponds to the type 2 superconductivity. And if you consider the opposite case, then this one becomes attractive and the Taiwan. Now I consider the next situation, which means two stacked vortices, which one has N1 vortices and the other one has N2 vortices with large separation at x1 and x2. This is, you can imagine like this, but these are not vortices, vortex and anti-vortex. I just borrowed the figure. So then intriguing question is, again, the interaction between these two vortices with a large separation. Then I employ the Abrikoso ansatz, which means product of the scalar magnitude and the addition of the scalar phase and the addition of the gauge field, which means this ansatz is valid only up to some level. So then under this large separation, the interaction energy between two stacked vortices are defined by the total energy subtracted by the energy of the single stack and the second stack can be written like this. So then the leading interaction terms are quadratic, as you see, different from the n superimposed vortices. Then interaction density become two vortex stacks is introduced like this. Then if you compute the one, then you can write in terms of the you may use it is written by the modified Wessel functions. So if we integrate out this x and y, and finally we have this expression, which shows this Higgs interaction is attractive and the gauge interaction is positive. So, which means repulsive. So then nowadays we are doing some numerical work for arbitrary separation because this expression is valid only for the large separation. And then I'm constructing the vortex-vortex interaction potential in terms of this separation. And what is the implication of this result to the cosmic string? So as I told you, the problem is if you have too many cosmic strings means density of the number density of the cosmic string is too high, then it collides with CMBR, so you cannot keep the cosmic strings. But if you have too small number of cosmic strings, then it may be impossible to observe the gravitational waves from the cosmic string. So if you consider the Taiwan's cosmic string, then because of the attractiveness, if their speeds are small enough, which means almost non-relativistic, and then they merge. So then the number density of the cosmic strings will decrease in the universe. However, if they form a cluster, and then it will emit the energetic gravitational waves. So if we have some chance, then we can easily get the gravitational waves, which is similar to the Taiwan superconductivity, in which the vortices are not important, but if you have small number of vortices which are merged, and then if they emit something, and then the signal is large enough to detect. So this simple conclusion, which can avoid the CMBR constraint, is my conclusion. Thank you.
Questions or next?
Do you have some estimate on the amplitude of the original wave dependence on the emission rate, the collision rate of this?
I'm starting.
What is the possible frequency region for the gravity?
Just what I know is usual cosmic string was tested already. So when we have the cluster, then the gravitational wave can be detected. What my main goal is to reduce the density of the number density of cosmic strings.
You mean the gravitational wave means two black hole mark?
No. If you have, for example, two things, for example, produced, and then they collide, and then if a cluster is made in a cosmic string, and then they burst gravitation.
So you are expecting this effect exists even after this inflation?
Okay, so any other questions? Next. Okay, next. Is that speaker name?